Hey y'all, this is a quick video to run you through how to use the solver functionality in Excel to fit nonlinear data. A lot of data that you see in your future career as a scientist will not be linear, so you can't use the traditional data fitting modes of Excel to get useful information. Instead, you have to develop an algorithm to fit that nonlinear data that's meaningful for your experimental system. In this lab, Dr. Fernandez has given you an equation that allows you to determine your dissociation constant, KD, from some experimental data. This equation is shown here. So our goal in this video is to use this equation and our experimental data to determine the best KD for this experimental system. Okay? And the first step to doing this is to use your experimental data to calculate an estimated DF over DF max for a given concentration of RNA and a KD. Okay, so from this equation, we have seen that if we can estimate a KD, then we should be able to calculate what this DF over DF max is based on any given RNA concentration. Okay, so I'm just going to start off just by putting in some random number for a KD. I'm just going to choose 10. Okay, so if we have a KD and an RNA concentration, then we should be able to calculate a DF over DF max. So I'm going to call this calculated. Okay, so the equation tells us that DF over DF max equals the concentration of RNA, that's my cell A2 here, divided by the concentration of RNA plus KD. Okay, so hopefully you've all used Excel enough to know how to use the equation part of this. Okay, and the one thing that you definitely need to add in is you're going to want to add in a $ onto I2. This is called a string parameter, and it tells Excel not to change the 2 when you copy this equation into other cells. Okay, so the reason that we want to do that is that we want to calculate the DF over DF max for each of these different RNA concentrations. So we want to do it for 10 and 20 and 50 and 80. And instead of typing in this equation every single time, we can take this cell and copy it. Okay, so by clicking on this little cursor in the bottom right corner and dragging down, I've calculated the DF over DF max for each concentration of RNA. And what you'll note here is, so in this cell, it's A2 I'm using and I2. In the next cell, I'm still using I2, but now I'm using A3. And the reason that the 2 didn't update in I2 is because I put that $ there. Okay, so we can calculate what the DF over DF max is for a given RNA concentration and an estimated KD. Okay, so up to this point, nothing should be especially difficult or surprising. It's things that you should probably have been able to do already. But now is where we're going to move into perhaps some new things. All right, so the first thing that I want to do is I want to plot my experimental data, the DF over DF max, and compare that to my calculated and see how close they really are. And when I do this, I always set it up where I have a separate entire grouping. If you like using Excel and creating graphs in a different way, do whatever works for you. But so I'm going to go ahead and just set it up so I have my concentration of RNA. I'm going to have my experimental data, and I'm going to have my calculated data. Okay, so the experimental is equal to this column, and the calculated is equal to this column. And we can copy all of these down for all the data points. So a couple more lines here. All right, so I'm now in a place where I can use all of this data. I'm going to insert a scatter plot. So the idea here is that the calculated should match the experimental almost perfectly if my KD is correct. Okay, and it's kind of hard to see when you have them both as scatter. So one thing that I like to do, so if you double click on one of the series, I'm going to go ahead and change this to a solid line. I like to make it red. And I want to have no marker. So this way I'm looking at the calculated or my fit data as a solid red line, and I can easily compare that to the experimental data, which is the blue circle scatter plot. And what you can see is it really doesn't fit that well. There's all of these points in here that there's significant deviation. Okay, and the way that we are going to quantify that deviation is by setting up a new column here that we're going to call our difference squared, or you might see it sometimes as R squared. Okay, so all we're going to do here is I'm going to set up an equation where it's equal to the difference between the calculated and the experimental. It doesn't matter which way you go because we're going to square now. So the difference between those two values squared. This is our R squared. And I'm going to copy this for all of them. Okay, so this difference now represents how similar or different the calculated value is from the experimental value. And if our KD was perfect, then all of these values would be exactly 0 because the difference would be 0. However, we see that's clearly not the case. Okay, the last mathematical step we're going to do here before we implement the solver function is I'm going to go ahead and set up a new cell here that I'm going to call the sum of squares. And this is this is going to be the sum of all of these R squared values. So equal sum, and I'm going to add all of these up. And the last thing I'm going to do is take this times a really big number. Okay, so I'm just doing 1 times 10 to the 15th. And the reason I want to do this is I want to magnify it. I want to make it as big as possible. Because the way this solver function works is it's going to try to minimize this sum of squares. Because minimizing the sum of squares means we are minimizing the difference between our calculated values and our experimental values. And if those differences are minimized, then that means the KD is as accurate as we can possibly get it. Okay, so we have set up our spreadsheet now to do exactly what we want it to do. We want to change this KD until the calculated values match the experimental values. Okay, and that's numerically represented by minimizing our sum of squares. And just to show you how this works, I'm going to go ahead and change my KD, let's say to 1. And what you'll notice here is on the graph, it deviates even further, and the sum of squares increased. If I change my KD to 100, it's starting to look better, but the sum of squares is still pretty large. Okay? And so you can go through this process and manually go through and change your KD as many times as you want and try to minimize this sum of squares. But that would be inefficient. And that's where this new functionality comes in. Okay, so it's called the solver function. And if you already have it installed, it's going to be under data and you'll see it under analyze. So this is the solver function. Most of you, if you're using a personal computer, it won't already be installed. So if you're using a Windows machine, you can do this by going to File, Options, and then on the left side here, there's Add-ins. Click on Add-ins, and then Manage Excel Add-ins. Go. You want to make sure that this Solver add-in box is checked. And then click OK. And now if you go to Data, the solver will be there. If you're using a Mac, I believe it's under the Tools or Options header. If you click on it and go all the way to the bottom of that menu, you'll see that there's an add-ins option that you can click and then add in the solver. Okay, but so we now have the solver installed, and the final step is to use solver to minimize our sum of squares. Okay, so I'm going to go ahead and put my cursor on the sum of squares. I'm going to open up the solver tool, and our objective is the cell that we're trying to minimize. So I want to make sure that it's set for, in my case, J2, or in your spreadsheet, whatever it may be. I want to minimize this. I could also select to maximize it or set it to a value of whatever I want. I want to minimize it. And I'm going to do this by changing a certain cell. And I'm going to try to minimize it by varying or changing my KD. Okay? So what this tool is going to do is it's going to change KD until the sum of squares is at an absolute minimum value. Now go ahead and click solve. It's going to think for a little bit. It's going to bring up this box asking if you want to keep it or restore it. We're going to keep it, so click OK. And then what you'll notice here is that your KD has changed. It's now at about 80. And this, whatever your concentration unit, will be the unit here, whether it's micromolar or nanomolar. Okay, you see the sum of squares is still pretty large, but that's because we took this value times a huge number. Okay, but so the idea is that this is the best it can get. We can try this again just to make sure it converges on the same value. So put in a 1. We've already seen that 1 doesn't fit the data very well. Let's try running solver again to make sure that it converges on about 80. So under data, solver, our objective is the sum of squares. The variable we're going to change is our KD, and solve it. And when you do this, you see once again it converges on 79.89, so right around 80. All right, so that's how you use solver to apply an equation to experimental data to obtain useful information. This tool, this solver tool, can be used for absolutely anything else. In other classes, like in other biochemistry experiments, you can apply it to like Michaelis-Menten kinetics, so that you can fit direct kinetic data to figure out your Km and your Vmax, instead of using the Lineweaver-Burk plot.